the title, you know, it is here. And now today we will talk about inverse problem. It is relatively new, the inverse problem of determining the order of fractional derivative in some differential equations. In last 10, 15 years, this type of inverse problem has received a lot of attention by many mathematicians, and a number of interesting results have been obtained. And there is a survey paper which is here, which is published in 2019 in a well-known handbook, and authors is Li, Liu, and Yamamoto. We'll give a brief overview of the most interesting works in this area and propose a new formulation for this problem and show how we can solve this problem, inverse problem. So, okay, let's consider the following inverse initial boundary value problem, 1 and 3. Here, derivative is taken in the sense of Riemann-Liouville. This is Laplace operator, boundary condition in the sense of Neumann, and this is initial condition. So I just recall the known definitions. So if we put d as a classical derivative, then this is Riemann-Liouville integral, fractional integral, and this is fractional derivative in the sense of Riemann-Liouville. And if we swap here differentiation and integration, then we got different derivative in the sense of Caputo. So you may ask here that does this you see non-local condition, and you may ask, does it have some physical meaning, this condition 3? And in the paper 2, the author shows that this is really have some physical meaning, and also we can obtain this quantity from measurements. So we will call this problem 1 to 3 as a forward problem. And you see, it often happens that this parameter is not known exactly, but we know that this parameter lies in this interval 0, 1, but we don't know exact value. And unfortunately, there is no device to measure this parameter. And that's why we have to solve it analytically, solving first problem. And it is important to know this parameter, because otherwise we cannot solve this equation and problem, and also we cannot investigate properties of the solution. So now, how we came to this problem? In 2020, when pandemic began, Professor Hugh Marov from New Haven University and Yang Quan Chen from University of California, they start creating mathematical model of spread of coronavirus. And it turned out that the system of differential equations which models this process is nonlinear differential equations of fractional order. And data presented by Johns Hopkins University on COVID outbreaks showed that this parameter rho lies in this interval 0, 1. And to find this exact value, Umarov proposed to search this mathematically, analytically, and we, together with Umarov, started to do this problem, to solve this problem. First, I would like to draw your attention in the following thesis of Professor Pshu, which is also participated here. It is believed that the first works that studies these such inverse problems published in 2010. But recently, Professor Pshu gave me a copy of his thesis, which from international conference, which is called 2002, where the author solved the following inverse problem. So here, this you see ordinary differential equations with fractional derivative in the sense of Riemann-Liouville, and you have two overdetermination conditions. Of course, T0 is not equal to T1, and then the author showed that you can uniquely restore this parameter rho. Well, but unfortunately, he didn't publish this result. Okay, now, as I told that there is a survey paper by Yamamoto and others, and after this, it was published in 2019. Before that and after that, there are many works published about this inverse problem. We will not stop on each of these papers, but we make several remarks. First, this, in all publications, authors consider only the Caputo derivative. And second, the derivative lies in between 0 and 1. And authors considered only homogeneous equations, and spectrum of elliptic part is discrete. And authors proved only uniqueness of this solution of this inverse problem. Of course, uniqueness is important from application point of view, but mathematically it is also interesting to show that in fact this solution exists. And last one is the authors considered the overdetermination condition in the form of 4. Almost all papers use this overdetermination condition, where x0 is from the domain omega, where you consider this differential equation. So, and also authors used asymptotic behavior of Mittag-Leffler function, and that's why capital T must be large enough. So on the other hand, you see, you are looking for one number rho, and you must know only one number instead of function, which is in condition so 4. That's why this condition is not very good for this inverse problem. And we will change this condition 4 and give another condition, and we will got another formulation of inverse problem. And in this, and we also show how to prove this, how to solve this problem. And with this new formulation, we can prove not only uniqueness, but also existence also. And also, we should mention that we can consider, instead of Caputo, derivative in the sense of Riemann-Liouville, and rho in our case can be larger than 1, and we can consider inhomogeneous equations, and also elliptic part is not necessarily discrete spectrum. And the main thing is that we change this condition 4. So now, okay, so what's this we change? Okay, now let's recall this inverse problem, which people consider it. Just a moment. We call it inverse problem 1. It is
Ashurov, can you put it full screen, please? I see only half of the page.
Oh, really?
Yeah.
Really?
Personally, yeah. So I don't know why it is
just a moment. Bring down full screen.
Oh, that's full screen. Yeah. So it is like that. So it's okay. Fine. Thank you. Fine. It's okay.
Ravshan, microphone, please.
I'm sorry. Okay, so this formulation of inverse problem, which was considered by other researchers. So first 3 lines, it is a forward problem, and this is overdetermination condition. Of course, you may ask that, can we restore this parameter rho for arbitrarily given h in this formulation? The answer is no. Why? Because you see this here, x0 is in the domain omega, where you have equation. That means h of t must be trace of solution of this equation. So this means h cannot be arbitrary. On the other hand, solution of this equation is infinitely differentiable with respect to t. That means H also must be infinitely differentiable. If you consider this inverse problem in this formulation. And because of this, in this survey paper, which I mentioned above, they put open problem. Is it possible to investigate the inverse problem using the value of solution at a fixed time t0? And for our part, we would add that once we are looking for one number, we should indicate only one number. Based on this consideration, we propose the following overdetermination condition in the form of 6. Here, f is some functional, not necessarily linear. So this function solution depends on rho. That means on the left-hand side, we have function of rho, f rho. So this 6 you can rewrite in the form of 7. So now, if you want to find rho from this equation, then if you can prove that f rho is monotone function, then everything is fine, that you can restore this rho. And this 0 cannot be arbitrary. It must be on the range of this function f. That is, it should lie here. And if it lies here, then you can find rho from this equation. If not, then there is no solution of this equation. Now, problem is how to find this functional f. So this first option, this is we call inverse problem 2 in the form of 8. So again, first 3 lines, it is forward problem. And this is, last one is overdetermination condition. Here we take solution of this problem and put here t0, fixed time, and get this scalar product, V1. What is V1? V1 is first eigenfunction of the following spectral problem. This is quite a simple spectral problem. And then this is Neumann condition. If you put here constant, then it's okay. You have this condition, it's a 0. And if you put here constant, then you have 0 and lambda must be 0. So first eigenvalue is 0. Okay, now to solve this inverse problem, we should have a solution of forward problem. Solution of forward problem depends on the function Mittag-Leffler function, which has the following form. And this forward problem has this solution. And now we want to find f, function f. To do this, we multiply this sum by first eigenfunction. And eigenfunction is orthogonal to all other eigenfunctions. That's why in this sum, you have only one term, first term. And when you put here 1, here lambda 1 is 0. That's why you have the following. This is very simple function. It's nice function. And now solution of inverse problem follows from this lemma. Lemma says that this function is strictly monotone and this condition 10 holds. So now to solve this equation to find rho, and this is monotone, and when we can have solution, if and only if d0 lies here, that you can formulate, this means in our case, it's equal to 11. So theorem says inverse problem 2 has unique solution if and only if this number d0 satisfies this equation, inequalities. Here phi1 is first coefficient of function phi. Okay, now this result was published in 2020 together with Umarov. And in this problem too, one can consider non-homogeneous subdivision equations. And this non-homogeneous case was published in paper 4, which is published 2021. We can also consider fractional wave equation, and this published in 2023 with Sitnik. This is Russian mathematician. Well, in all other, these papers, we considered Riemann-Liouville derivative, and also we demand that lambda 1 is equal to 0. The idea in these papers same as above, but the only thing is it is technically more difficult. Because, for example, if we consider fractional wave equation, and rho is in between 1 and 2, then you have two initial conditions, and then you have, instead of one function, you have two functions. Even when you have f is right-hand side is 0. If you have right-hand side, then you have here one more term. You see, above we had only one function of rho, and to show this is monotone, it's not that much difficult, but when you have two functions, then you must investigate two functions and compare this derivative of these functions and show that it doesn't change sign. Right. So it is technically more complicated. Now, of course, instead of Laplace operator with Neumann condition, we can consider arbitrary self-adjoint abstract operator, but the only condition is first eigenvalue, not necessarily first one. Any of them, uh, it's enough. One of eigenvalues is 0. Okay, but this method has some disadvantages. First of all, lambda 1 must be equal to 0. And secondly, with this method, we cannot solve this problem with Caputo derivative. Indeed, if we consider inverse problem with Caputo derivative, then solution will have the following form. And after multiplying V1 as above, we have this result. You see here, Mittag-Leffler function, rho 1, that just classical one. That's why this when argument is 0, this is 1. So you have this equation to find rho doesn't have rho. That's why in the case of Caputo derivative, this method doesn't work. Now we give another method in which we can remove this condition, lambda 1 is equal to 1, and also we can consider Caputo derivatives. Okay, now this problem we call inverse problem 3. So again, first 3 lines as before, this is forward problem, and we have additional condition in the following form. This is just norm of solution of this equation. You should note that at fixed time t0, you see, as it was in open problem in survey paper. So if you have this norm d0, then you can solve this inverse problem. That is, you can find this rho. In fact, this solution of this inverse problem follows from this lemma 3. Lemma 3 says that this function, as a function of rho, is monotonously decreasing function. So once this is the monotonic function, then this equation will have the only solution if and only if d0 lies in between these two numbers. So this is solution of this inverse problem. Now, this theorem was proved in this paper, AAM of Ashurov, which is published in 2022. And a few words how we can prove this lemma 3, this one. So how we can prove that this is monotonously decreasing function. So to do this, we just again see solution at fixed time instant t0, and then take norm, and using Parseval equality, we have the following formula for this norm, right? And now, if we show that this function for all lambda k as a function of rho is monotone and positive, then you have a solution of this inverse problem. So in fact, our lemma 3 follows from this lemma 5. So it says that this function is a monotonically decreasing function for large enough t0. large enough T0. So to prove this, we just need to show that derivative of this function with respect to rho is negative. So how we do this? We introduce Hankel path. It is well known. So in this book by Jargishan, it's proved that this function which we want to investigate has this form 13, where beta here in between these numbers arbitrary. So we can choose beta just like this. This number is in between these two numbers. This is fine. Now we should investigate derivative of this function with respect to rho. So it is technically difficult, really, because this, you see everywhere you have rho here, rho here, rho here, and also the most important thing is that the region where you take the integration also depends on rho. You see, beta is equal to this, but still, nevertheless, you can show that the derivative is negative if you take T0 here large enough. So this gives solution of this inverse problem in the formulation of in 3, inverse problem 3. Now, with this method, you can consider also the case when you have Caputo derivative. When you have Caputo derivative, solution will have the following form, and norm is equal to this. Now you have different Mittag-Leffler function. And again, we must show that this Mittag-Leffler function. Can you hear me?
No. It's okay.
Mahmoud, can you hear me?
Yes.
Okay. Now, so in this case, you must show that this function is positive and monotonically decreasing. Here we use this formula, which is also proved in above monograph of Jarvishan, and then this function has the following form, and then we take derivative and show that this derivative is negative. And in the case of Caputo derivative, this result was published here, Alimov, Ashurov, 2020. Now, you see, we above considered the following overdetermination condition, but here we show that instead of this, we can take many other options for overdetermination condition. For example, for arbitrary function, which is defined like this, we can consider the following operator. And if domain of this operator lies inside the domain of operator A, then as a function f, we can take the following. And we can, for example, if you take this function square root of lambda, then f will have this form, and this is full energy of system. You can calculate it easily as an overdetermination condition. And if f is lambda, then you have norm of A, operator A, and this last case we considered above. Now, well, sorry. Yes. Now we will consider the case when elliptic part has a continuous spectrum. So you see, we consider this problem in Rn, and then this operator, elliptic differential operator with constant coefficients. It's known that this, if you consider this in Rn, it has continuous spectrum, and solution of this forward problem has the form 16. And this problem we considered in this paper, Ashurov, it was published 2020. And now the main thing is that here, how to give overdetermination condition. So overdetermination condition we take as follows. This Fourier transform of solution, and at one fixed point, and xi0 is taken with these conditions that xi0 is positive, and phi function at this point is not zero. Then we can prove that the inverse problem has unique solution if and only if D0 satisfies this condition. Now, you see, there is a Rayleigh-Stokes equation which has this form, and it plays very important role in describing behavior of non-Newtonian fluids. And in recent years, this problem has received much attention, and you can see these papers, and this is just some of these papers. And that's why we wanted to find out whether we can find this alpha derivative here. This is Riemann-Liouville derivative. Alpha is in between 0 and 1, and T0 is some point from this domain. We should take it as this point large enough. So we investigated this inverse problem. To do this, we should solve first forward problem. Forward problem solution is given in this paper, Bezhlikova, and it has this form. Capital B has this form, 19, and here B, small b, has this form. So this overdetermination condition can be written in this form. So before we considered here was Mittag-Leffler function, and now instead of Mittag-Leffler function, we have the following function. And the method is the same. Now we should show that derivative of this function, you see this how it depends with respect to alpha. You see here everywhere alpha, but still we can prove that if T0 is large enough, then derivative is negative. And this, in fact, solves this inverse problem. Now, we also consider the following mixed type equation. You see, now 21. If t is positive, we have here already Caputo derivative. Alpha is in between 0 and 1, and beta is in between 1 and 2. So this is so-called mixed type equation. This is boundary condition, this is initial condition, and this is gluing condition. This problem was first considered by Zhuzhansky and Karimov when n is equal to 1. They investigated inverse problem to find right-hand side of this when n is equal to 1. And in our paper here, 2021, we solved inverse problem simultaneously to determine alpha and beta, both parameters. To do so, we should first solve forward problem. A solution of forward problem has this form. Here t positive, here t negative. And here we first show that this denominator is positive for all k and t if t is large enough. And we put two overdetermination conditions because we have two unknowns, alpha and beta, here norm and here scalar product. In fact, you can take here also norm or here scalar product. In all the cases, you can solve this inverse problem. Now, we can calculate that F1 has this form, this first overdetermination condition, and second overdetermination condition has this form. You see, we have chosen this condition in such a way that, you see, this equation depends only on beta. And then, if you show that derivative of this function with respect to beta doesn't change sign, then you can uniquely determine here beta and put it here, beta, and solve this problem to find alpha. So this is, in fact, was done in that paper which I mentioned above. Now we will consider inverse problem to find right-hand side and rho. Such problem first was investigated by these authors in 2020. They considered this problem 24, where omega is disk in R2. This parameter rho is in between half and 1. And this is overdetermination conditions 2, x1 and x2. They both from omega. And the authors proved only uniqueness. And we, in this paper, 17, 2022, which is published. We consider the same problem. We take omega as omega arbitrarily n-dimensional domain with smooth boundary, and rho in between 0 and 1, not only here, but here. And we proved not only uniqueness, but we proved that both unknowns exist and unique. How we do this? We put two overdetermination conditions. This one to find the order of derivative, and this is to find right-hand side. And if so, solution of this inverse problem, finding three unknowns, exist and unique if and only if these conditions are satisfied. Now, now we will consider two parameter inverse problem. In 2013, Tatar and Ulusoy, they are from Turkey, by the way, they considered the following problem. This is equation. X is minus 1, 1, this omega domain. And this is one-dimensional fractional Laplace operator. And sigma here is in between these numbers, two numbers. Rho is in between 0 and 1. And they prove that if this initial function belongs this, and this is very strictly conditioned, all Fourier coefficients must be non-negative. And then the authors proved uniqueness of solution of inverse problem. So inverse problem here, two unknowns, rho and sigma. So Yamamoto in 2020 considers the same problem, but instead of one-dimensional domain, they put arbitrary n-dimensional domain, and instead of this overdetermination condition, this Tatar-Ulusoy was considered this overdetermination condition. 0 is inside the domain where you have equation, and Yamamoto considers the following way. But also Yamamoto proved only uniqueness of this solution of this inverse problem. That means both parameters, uniqueness. So we considered arbitrarily omega domain. Oh my God, sorry. Here, arbitrarily domain. And we put the following two overdetermination condition. And we proved that if D0 and D1 satisfy these conditions, then solutions is three unknowns, unique and also exist. And this was published in the following paper. This is 2024. And how we prove this theorem? These two overdetermination conditions can be written in the form of 26. So D0 and D1 is given numbers, and sigma and rho unknowns. So you have system of equations, two unknowns, and now you should show that this determinant is positive. If this determinant non-zero, if it is determinant 27 in non-zero, then both parameters exist and they are unique. So what we have done in this paper, we showed that we take this derivative, and calculate this how to call determinant, and show that it is not equal to 0. Now, this very interesting paper, Artushin, published in 2023. The author considers the following problem, inverse problem. Here, you can mention that rho depends on x, so on space, not on time, on space variable. So this is overdetermination condition, and under some conditions on right-hand side, and authors proved that if this function phi is from this Sobolev space and satisfies these conditions, then rho exists and also unique. I think this is first time when the author considered this inverse problem with not constant but variable order of fractional derivative. Well, now, yeah, you see, from here, you can mention that t must be small enough in this paper. So, but when we consider, in our case, this where we give overdetermination condition, t was large enough. That's why we just motivated from this paper. We also tried to prove our all theorems which we presented above for not sufficiently large T0, this, but sufficiently small. And to do this, we proved these following two theorems. This is just the main basic theorems for proving all above inverse problems. And first theorem about these functions, you see here, if you t is sufficiently small, this still is monotonically decreasing function for all rho. And also, when you consider Caputo derivative in the solution, you have this function. But when you consider Riemann-Liouville derivative in the solution, you have this function. And we also proved that if t is sufficiently small, then this function is monotonically decreasing function. So the method proving this, we borrowed from this paper, which is published recently, 2023. And the authors consider this function. Here, you see, we just removed c. And they proved that this derivative is negative if t is large and c is small. So here we removed this condition large t, but we proved for small t the same results. That's it, what I wanted to tell today. Thank you for your attention.